Today we are going to see how pointers can help us in accessing a one-dimensional array. So, the topic is the relationship between one-dimensional arrays and pointers. We can try to understand how a pointer can be used to access a one-dimensional array. So, let us look at an example. Here we have a function foo which declares an unsigned array of 5 elements, and here note that when I am using a scanf statement to read an element of the array, we know that we have to pass the address of the ith element for all values of I from 0 to 4 in this case. But here I am passing that address as ARR plus I, which is a new syntax that we are discussing today. And what is it? Actually, this expression ARR plus I represents the address of the element at index I. So, it is equivalent to ampersand ARR square bracket I. So, this is what I am telling. It is a pointer. ARR plus I is a pointer to the unsigned value stored at index I in the array ARR. So, it is an address of the element ARR I, and hence it is a pointer to the ith element in the array or element at index I. That is, ampersand ARR I and ARR plus I are the same. They both represents the address of the element at index I in this array. So, now this is a pointer notation because it represents the address of that element. Now, suppose you execute this program or a function or this function, you know that an activation record will be created on the program stack, where memory will be allocated for all the automatic variables or data objects. Here there are 2 data objects which are automatic. One is ARR, which is an array of 5 elements. Each element is assumed to be represented using 2 bytes in memory. So, these are the 2 bytes. This is memory address and this is the index of the first element. So, the first integer, unsigned integer, is stored at memory location 100 and 101. The value is unknown because it is not initialized. And also there is an unsigned integer I, this is I, that is again getting 2 bytes of memory. And other than that, the activation record is having a location 2 bytes for storing the return address. I assume that the address is again 2 bytes, and here there is a pointer or address of the previous activation record. Now, if you look at this expression, what are the possible values for different values of I? When I is 0, ARR plus I is 100, that is the starting address of the array or address of the element at index 0. Now, what is ARR plus I for I is equal to 1? The address of the element at index 1, the address is 102, and likewise it goes. Now, if you proceed down in this function during execution, then you are going to print this message, enter 5 numbers, then the control comes to this loop, and where you are trying to read elements into the array. So, the user must have to give 5 elements. Suppose you are giving these are the elements, then the loop can finish, and not that what it is doing is reading these elements into the positions 0, 1, 2 and 2, 3 and 4 in the array. Not that now the value 5 became 5 and control goes out of the loop. So that's it, and I hope you're getting what I am telling. If you recollect, ARR is defined as pointer constant. You can say that it is a pointer constant. Why is it a pointer? Because ARR is nothing but the address of the first element of the array. ARR is nothing but ARR plus 0. ARR plus 0 is the address of the element at index 0, which is 100. In that sense, it is a pointer because ARR is the address of the element at index 0. In that sense, it is a pointer. Then question is, then why is it that it is a pointer constant? Because the value of ARR in this particular case 100 cannot be changed. That means you cannot have an instruction like this. This is not allowed. You cannot assign the address of any other location into ARR, which is not allowed. And that is why it is known as a pointer constant. Why is it that it is a pointer? Because it is the address of the element at index 0. ARR plus 0 is ARR. And it is a pointer constant because you cannot alter the value which is 100. Okay. And this is what we saw. ARR points to the first element of the array or the element at index 0. Now, suppose PTR is a pointer, maybe a pointer variable or a pointer constant. Then what is this expression representing PTR plus I? We can try to understand. It's not just an addition, something else. It is actually a symbolic representation, and we will see what is that symbolic representation. Look at an example. Suppose you have a function, say foo, in which you are declaring an array with 6 elements, and not that a pointer is declared of type unsigned. So you can assign the address of any unsigned integer to PTR, and in this particular case you are assigning the address of the unsigned integer at index 2 in this array. And if you look at the execution of the function containing these two, an activation record will be created where an array of 6 elements, index value 0, 1, 2, 3, 4 and 5, and you also have another automatic variable which is a pointer variable, and it is getting the value which is the address of the element at index 2. At index 2 the address is 104. So you are getting it here. And then you have positions in the activation record for storing the return address and also the address of the previous activation record. And now if you look at what is PTR, PTR value is 104. So PTR plus I, when I is 0, is 104, the same address. And you can see that PTR plus 1 is the address of the element in the next position. In the next position it is 3, index 3, and the address is 106. And if you look at PTR plus 2, it is nothing but the address of the element in the next position, or 2 positions away from the current position of PTR. The current position of PTR is at index 2, plus 2 means 2 positions away, that is the address of this. Likewise it goes. And if you want to look at what we discussed, if PTR points to the ith element of an array, then PTR plus 1 or PTR plus plus, you can increment like that also, points to the element at index I plus 1. That is what we see. And in place of I you can also use negative integers. If you look at -1, you can see that PTR is pointing to the element at index 2. -1 means this address, that is the element stored one position before the element at PTR. Similarly, if you look at IS -2, it is the element stored two elements before the current element of PTR, that is the address 100. Okay, I think you are getting me. So, this is what we discussed. If PTR points to the ith element of an array, then PTR -1, or you can say PTR -1 decrement points to the element at index I -1. So, if the PTR is pointing to element at index 3, PTR +1 is the address of this element and PTR -1 is the address of this element. Okay. Now, just look at one more example before we formalize. Here the only difference is that it is a floating point type. So, three elements are there. If you execute, each float value is assumed to take 4 bytes. So, this is the first index, second index, third index, 4 bytes each, and other than that there is a pointer. Now, see that in this case we are assigning the address of the index at 0. ARR is the array name is a pointer constant, which is nothing but the address of the index at 0 in that array. So, 100 is there in the PTR. And here you can see that PTR plus I means 100 when I is 0, plus 1 means the address of the next element, which is 104. Plus 2 means address of the element at index 2, 2 positions away from the current position. And if you generalize, you can see that when PTR is a pointer variable or a pointer constant, then PTR plus I is a symbolic representation of the memory address, which is I locations away from the memory address stored in the pointer variable PTR. Now, in this example, PTR stores the address of the element at index 0. So, what is PTR plus 2? Elements stored in this array 2 positions away. This is the element 1 position away from this. This is the element 2 positions away from this. Okay. And if you want to look at it mathematically, you can see that the expression PTR plus I represents this numeric value, which is PTR plus size into I, where size is the number of bytes required to store a value of the data type of PTR. For example, here data type of PTR is float, it requires 4 bytes. So, if you put I as 1, it is PTR plus size is 4 into 1. In this case, PTR is 100. So, 100 plus 4 into 1 is 104. And what is that for? Number of bytes required to store an element. And if you look at here, then PTR plus 2, what is it? PTR is 100 plus size is 4 into 2 is 8. So, 100 plus 8 is 108, which is exactly the address of this element. And why is it that it is 2 into 4? Because it is 2 elements after. For each element you need 4 bytes. So, for 2 elements you need 4 into 2 bytes, and that is the significance of size here. So, this is actually the numeric formula representing this, and this is only a symbolic representation. If you just add I to PTR when I is 2 and PTR is 100, you will only get 102, but it is not like that. This is the actual numeric formula representing this, and depending on the data type, this value changes. If it is 2 bytes, then 2 into I. If it is 4 bytes, then 4 into I, and if it is 1 byte, then 1 into I. So, that is the relationship between pointer and single dimensional array. And let us proceed. One dimensional array and pointer notation. Now, we can look at an example. Here you have an array with 6 elements unsigned, and if you look at the execution of the function, say foo, in which this is declared, when that instance is created, it is getting an array with 6 elements and all these values are stored, then the return address and the address of the previous activation record on this activation record, and this is what we saw. So, for all values of I from 0 to 5, what is ARR plus I? The address of the element at index I. When it is 0, the address is 100. When it is 1, the address is 102. Likewise, it goes. So, what we are telling is ARR plus I is the address of the element at index I. So, these two are same. Now, if you want to look at the values, you can say that if ARR plus I is a pointer, from the previous lecture you know that you can get the value by an interaction operator, that is the value stored at this address. What is ARR plus I? Address 100. What is the value stored at 100? It is 10. What is the value stored at say 106, which is ARR plus 3? The value stored at 106 is 40. So, that is it. Please do not get confused. Here what we are telling is that ARR I is the usual syntax we use to represent the value, and which is same as star of ARR plus I, because this is the address of the element at index I. So, in that way it is a pointer, and using pointer, this is how you access the value. Okay, now we have two equivalent representations for the address of an element in the array and also for the value of an element in the array. Okay, I hope you are following me. It's a very important concept, because when we use pointers to access array, you need to have a clear picture about what all these things are. And if you are not able to follow, please watch it again, and for the interest of time, let me proceed. Now we are going to see how can you use pointers for passing an array as an argument. Okay, and we are not going to introduce any more concept today. We are just going to apply what we have seen in this slide. You can access it using a pointer. That is what we are going to learn, and note that the name of the array is a pointer constant, which is the address of the element stored at index 0 in that array. So, it is actually a pointer. Now, you look at an example. Here you have a function foo, which is declaring an automatic variable I of unsigned and an array with 3 elements unsigned, and the elements are also initialized to 1, 2 and 3, the only 3 elements, and immediately after the declaration it is calling a function with the array as the argument. So, you are actually passing the address of the first element in the array. So, how can you catch it in the function bar? It must be a pointer. It must be a pointer because it is an address. Later we can see the array notation that we used to have in our previous programs. Now it is a pointer, and that is fine, because here we are passing the address of the element stored at index 0, which is the address of 1, which is an unsigned integer. So, definitely the address can be caught in an unsigned pointer. And now here you note that I am accessing the element using both these notations, both are same. This is the element at index I, this is again the element at index I, using pointer notation, and here using array notation. Let us see how this program executes. So, this is what we already know. PTR plus I star and PTR I represent the same object, and in this particular case what is it representing is the element at index I in the array ARR, which is defined in main. Note that PTR is a local variable in bar which is getting the address of this array, and hence By using these notations, you are able to access the elements of this array. Let us see how you execute. If you start executing this function, you know that these two will be allocated memory on the program stack. ARR is an array of unsigned integers with 3 elements. These are the elements initialized, I is not initialized, and you have these two for return address and for the address of the previous activation record. Now, if you proceed down, you are coming to the function call, you know what is going to happen. The control will be transferred to this function. So, an activation record should be created on the stack, and in this case only 2 local variables are there, a pointer and an unsigned integer. So, that is what is happening. The pointer is getting 2 bytes, and what is it getting as value in PTR? The value which is passed by ARR, which is nothing but the address of the element at index 0. So, 100 is passed to it, it is getting 100, I is uninitialized, so I do not know what it is. And the return address, when you return from this function, it has to come to this particular instruction, so it is alpha. And this is the address of the previous activation record, because this is the previous activation record. Now, if you proceed down, you can see that what you are doing, you are actually accessing that element at index I, and you are just incrementing it. I am using 2 different notations, this by using pointer notation and this by using array notation, but I am accessing the same element. So, I am just incrementing. Now, it is 1, 2, 3. If I finish executing this, it will be 2, 3 and 4. Yes, 2, 3 and 4, and I becomes 3, it comes out. Now, you are going to return, that means this particular activation record will be taken out from the stack, and you will return to alpha, because alpha is here, and the new activation record will be the next one. So, that is what you can do, and note that the function bar modified the elements of ARR in main through this pointer. Now, if you execute this return, then that activation record is deleted. Now, you came back to the calling function, and you are going to execute now this for loop, where you are trying to print the content of the array, which is now 2, 3 and 4. If you execute, you will get 2, 3 and 4 printed, and that program finishes its execution. So, this is how you can use pointers, and maybe in the next few slides we can connect it with the array notation. Okay. So, what we have seen is when we use pointer as argument to receive an array, so this is how you can do it. Here ARR is an array of 100 unsigned integers, and you are passing the address of the first element in the array, ARR, which is the name of the array, a pointer constant, and you are catching it in a pointer. And what is this pointer? It's a pointer variable which can receive the address of a memory location allocated to store the value of data type unsigned. So, by declaration, it can catch the address of any unsigned integer. And we know that PTR plus I or ampersand PTRI equivalently represents the address of the element at index I, so of this array. And also we know that these two are equivalent. You can access the element by using either the pointer notation like this or by using the array notation. And if PTR points to the element at index I, then we know that PTR plus plus will make the pointer points to the next element or element at index I plus 1. And if you want to look at the other representation, suppose you are catching it in an array here, so this is the difference, then you will declare, sorry, the star is a typing mistake, I should not have this star, okay, sorry for that, I will remove it before I send the slides. So, it is just BRR then this square bracket. Then you can have the same effect, the only difference is that then in place of PTR you can use BRR, okay. and not that star is not there. Okay, so without this star, now this is a pointer variable and this is a pointer constant. Okay, BRR is not a constant, because if you pass the address of this array, that can be assigned to BRR, or you can pass the address of another array, doesn't matter. So in this case, the formal argument is a pointer variable and the actual argument here is a pointer constant. And what we show is that yeah, here I have got it correct, the star is not there. So these two are equivalent. I can either have this pointer representation for the formal argument, or I can have this representation. Okay. Now I will show you just an example to see how can you use pointers to access the elements of an array without even using an index. Here is an example. So what I am doing is in foo I am declaring an array of 4 elements, and I am passing that as an argument to a function where I am catching it in a pointer variable. Okay. Then I am printing all the elements of this array using the pointer notation. So what is star PTR? PTR will point to the address of the first element. So when I print star PTR, I will get 1 printed. Then I am incrementing PTR. So what will it do? It will make the pointer pointing to the next element. So address of 2. Then I am printing star PTR means going back, printing it means I will print 2, 3 and 99. It goes like that. And here you note that this is just an example, not a good programming style, because here I am doing it until the content becomes 99. Star PTR is the content. Okay. So if you pass an array where 99 is not there, then this will become an infinite loop, or it will try to access a location which is not allocated to your program, and hence your program will crash in such a case. So this is not a good programming practice, but just for you to look at an example, how can you access an array using only the pointer notation without using an index. Not that PTR plus plus is PTR plus 1, which is the address of the next element in the array. Then next time when you access that element, you will get the next element. And with this, we are finishing this lecture, and I am giving you an exercise for you to practice and understand how pointers can be used to access a single dimensional array. So here is the exercise. You read it offline and try to find a solution for this. So with this, we are finishing this lecture, and today we have seen the relationship between one dimensional array and pointers. You can see that the address of the first element of the array is represented by the array name itself, and in that sense the array name is a pointer to the first element of the array. So you can pass it, or you can assign that to a pointer, then after you can use pointers to access the element. We have seen the syntax which is PTR plus I, then how to access the value using the interaction operator, etc. And I hope you are not very confused with pointers. Please try to learn it from the last 3 lectures, and if you are not able to understand, view it repeatedly and make sure that you are having a very sound basic about pointers in C. And with this, we are finishing our discussion on pointers. Thank you.